All right, so I'm Jeff Goodell. So I work here at UCL, and I'm going to give you a talk on the technology. Following on to Professor Asti's presentation, I'm going to talk about the technology that underpins blockchain and distributed ledgers from an abstract perspective. I'm not going to provide examples of how Bitcoin or Ethereum work. I'm going to stay focused on topics related to how distributed ledgers work in general and the kinds of questions that we have to ask. And I'm also going to describe some patterns and anti-patterns in the design and deployment of these systems. Please stop me at any moment if you have any questions, and I'm happy to talk about any topic that you might be interested in along the way, as long as it's relevant. And let's begin. Let's try this out. Hopefully I haven't forgotten anything from last year's talk on this topic, which is slightly different, but mostly the same. OK, so we all know what a ledger is. A ledger is an information store that keeps final and definitive records of transactions. And transactions are the smallest unit of a work process that results in a state change. So we think of ledgers as really representing some notion of a world state of the different parties who are transacting within a system. And a distributed ledger is just a distributed way to represent this rather than having one central owner. Now, we can't really talk about distributed before we talk about networks. So what is a network? Well, a network is just an interconnected system of things or people. And here are some classic examples from Paul Barron's work back in 1964. He shows an example of a centralized system where there is just one special hub point in the system, and everybody talks to that hub. And if the hub goes down, well, that's just tough. And everyone talks to that hub, so the hub is basically in control. Decentralized systems, where there might be multiple sort of mini hubs, but if one of them goes down, maybe some of the nodes in a local area might be broken, but not everyone is. And this notion of a distributed network, where the density of the degree of each node, or the number of connections that each node has in the system, is relatively small, and there is a sense of locality. So there might be a node that happens to be close to a few other nodes, and if something goes wrong in the system, it's isolated to one particular area, and it's not necessarily as efficient as a system like this, but it's more robust. So does anyone have any questions about this? Centralized, decentralized, distributed, and what the implications might be. Everyone's connected to one point, maybe multiple points, and locality. Okay, that's important. OK. Now, there are problems with centralization. Number one, the party that's in the center, so remember that centralized system graph that we just looked at, could censor or ban users of the system. So when Professor Asti talked about incentives versus sanctions, think about this as being the ability to apply sanctions. When you're in the center, you can run a blacklist. And you can use that blacklist to censor or ban. Simple. Second, rent seeking. So you can charge fees to use the system. So think about a toll operator, an operator of a toll bridge that might link two sides of a city. If there is only one bridge, then that toll bridge operator can perhaps charge a lot of money to cross between one side and the other. And that phenomenon is something that is enabled by their position in the center. Third, they can change the rules of the system. So maybe they don't charge a fee today, but they encourage the development, the construction of a bridge, and then tomorrow they charge a fee. So I like to use the example of Uber, and I think of Uber drivers getting subsidized by really wealthy investors, and up to the point that Uber rides might actually cost more than twice as much as I actually pay. However, at some point, the investors are going to need to make money, so I guess they're banking on the idea that something's going to change. Fourth, the central point might lie or tamper with the data in the system. So if we're talking about systems for the purpose of collecting and aggregating data, if you're sitting in the center of the system, you can change the state of the world. So we talked about the ledger from before and how that represents a world state. Well, if you're in the center of a centralized system, you can actually make the ledger, the state of the world, reflect exactly what you want, even if that's not true. And finally, that central party might actually be well-intentioned, might not want to create blacklists, might not want to seek rents, might not want to change the rules, and might not want to lie, but might make mistakes, might get hacked, might go out of business. There are a lot of problems. Enter distributed ledgers. Ordinarily, when we have a ledger, we have this clearinghouse that everyone trusts to be the central clearinghouse of perhaps an exchange or another marketplace. With a distributed ledger, rather than having all of the records held in one central place, the records are held across the entire system. So all of the different participants, or some fraction of the participants anyway, have complete copies of the whole ledger. So they don't have to ask someone in the center for what the record is. They already have it. That's a feature of the distributed ledger system that Professor Asti just described. Does this make sense so far? Any questions? OK. So let's talk about the motivation. So cryptography, I'm sure many of you are familiar with cryptography at some level. We talk about signing and encrypting messages, for example, in communication. Now, cryptography in general is actually about eliminating trusted third parties. So if I want to talk over a network or over a channel that might be eavesdropped or tampered with, I can encrypt my message so that only the party that I intend to receive the message can receive it. I can sign the message so that when the party does receive it, they know that it hasn't been tampered with. These are ways to use cryptography to eliminate trusted third parties from communication.
Sorry.
Yes?
Can you go back one?
Yes.
What you said there, I think is correct for native assets, not necessarily for other data, right? Because what's distributed is hashes, is not the actual data, right? While there, on the centralized point, you can have Facebook and your pictures on there, as opposed to hashes on the other side and your pictures on your mobile.
So let me have to talk about what a ledger is. A ledger is about transactions. Okay. So all that I'm talking about is transactions in a system. Now, would it be possible to encode data or other kinds of assets directly in this kind of system? Perhaps. But that's not really what I'm talking about when I'm referring to ledgers, because when I'm referring to ledgers, I'm referring to the transactions that make use of the system. So the changes, if you will, the changes of ownership, the changes of state. So let's separate the notion of a ledger from the notion of a database, which serves a different purpose, and we can talk about that separately. Is that clear? Okay, so cryptography is about eliminating trusted third parties. Blockchain technology, we talked about cryptography applied to communication. Now let's talk about blockchain technology as applying cryptography to transactions. So that's what I'd like to stress is really the motivation. So when Professor Asti said, well, what we're doing is we're combining two technologies that are actually quite old, centuries old even. We have blockchain and distributed ledgers on the one hand, and we have cryptography on the other. We're actually here applying cryptography to transactions. Now why? Well, we want to achieve certain properties. Decentralization, well, that goes back to the question of building this decentralized network and having no single point of trust, no single point of control, no single point that can impose policies, no single point that can create blacklists. We want security, non-repudiation and irreversibility of records so that they can't tamper with it. No one can change the truth without everyone noticing. We want reliability. That's just resisting the changes in manipulation in the first place. And we want auditability, which is being able to look at what changed, have everyone know when, have all the participants be able to verify that the records had been true without having to query externally. And this is really important. Because if we remember that slide with the ledger versus the centralized versus the distributed ledger, in the case of the centralized ledger, I need to do a query into a central system in order to determine whether something is true. With this distributed ledger, I've already got it.
Only that you just mentioned a few minutes ago that you're not talking about the records.
I'm talking about the ledger, the transactions.
Yeah, but the auditability, even if you verify don't know that word.
The veracity,
What's for us?
the correctness and truth.
Yeah, so they can't actually, because you were just saying that it's not about the database, it's about the transaction
Well, the records in this context are records of transactions.
of transaction.
Yes. So if there's one thing that is clear, ledgers, databases, different problems. They solve different things. So we'll talk a little bit later about some notions of DLT and what it's for, misconceptions, and what this is really about, and we'll get to that in more detail as well. Okay, so let's take the bird's eye view of the system. What are the different parts of a distributed ledger system? Or what are the different aspects of it, I suppose you could say? Well, number one, there's software, which implements a protocol. And the protocol is what needs to be agreed upon, ultimately. Often the protocol is the software, implicitly. So for example, if you want to run Ethereum, there is of course, the Ethereum Foundation, I believe, actually controls the path of the software. There are groups in Bitcoin that do the same, more or less. That there are de facto parties who control the software which de facto implements a protocol. Although it's possible to build a protocol via a multi-stakeholder process, like a standards body, for example, but that's a different kind of approach. The point is that the software implements a protocol. You need a design for the ledger itself. So how is this ledger constructed? You can have blockchains, yes, but there are also other kinds of systems that are also distributed ledgers. You could have, for example, generalized directed acyclic graphs like IOTA or tangles. Systems like Stellar. They use systems that are not, strictly speaking, blockchains, but they are distributed ledgers. So that design of the data structures. Third, you need a consensus model. We talked a lot about consensus in the last hour. Well, what does it take to have consensus? Maybe it's a 51% majority, maybe it's an 80% majority. Maybe it's a vote. Maybe it's a vote within a local area, maybe it's a vote in a larger area, maybe it's the whole system, maybe it's elected representatives. How do we build consensus in the system? And finally, there are applications. Applications that sit on top, or applications of the system. We've talked about this in the context of cryptocurrency, yes, but there are other applications as well. Professor Asti mentioned supply chains. And there are a host of other possible use cases, perhaps medical records, perhaps multi-party negotiations of legal documents. The list goes on and on. And Lord Holmes, here in the UK, had actually recommended an exploration of the many uses or many applications of distributed ledger technology beyond cryptocurrencies, explicitly for the purpose of involving many industries in the design and development of this technology. And there are many uses. This doesn't seem to be working anymore. I guess it's dead. Oh well. No matter. All right, well, I don't know what to do. Maybe someone can help. But in the meantime, I'll just use the right arrow. OK, so blockchain. There we go. That's better. Data structure comprising the transaction records. So we talked about transaction records. And additional data that includes a cryptographic link to the previous block. Now, we can talk about the definitions. There are different groups of parties. I'm going to give a lot of definitions. They're not necessarily official definitions. In fact, there are groups that are working to determine what these definitions ought to be. It's such an active field. There is still some dispute. But this is generally agreed upon. Now, what is the link? A cryptographic hash function. We talked about hash functions. They're one-way functions from some data blob into some random number. So we have these transactions, and I'm just going to simplify it relative to the last presentation. So hopefully this will be clear. Many transactions and the hash of the previous block. So that's what creates this relationship between this block and the next block, and so on in a chain. So a blockchain is a distributed ledger with confirmed and validated blocks organized in an append-only chain with cryptographic links. There's a genesis block, which is block 0, the one that links to nowhere, or perhaps itself, depending on the implementation. And then the next block gets built pointing to the first block, and subsequent blocks, and so on, forming the chain of all transactions. Now, some of you might know about a theorem, which in computer science is known as the CAP theorem, which means that systems cannot be globally consistent, immediately available, and tolerant of network partitions. You can only choose 2 out of 3. Most implementations of databases choose tolerant of network partitions and globally consistent, at the risk of sometimes being not immediately available. Database might say, not ready. Blockchains are different. They have to be tolerant of network partitions, but rather than choosing the other feature that's desired as global consistency, they choose availability. So different nodes, as I think one of you had mentioned, might not necessarily all have the same view. So that means that some people might believe that the blockchain is this, 3A, 2A, 1, 0, and other people might think that the blockchain is this, 2B, 1, 0. And these different views of the chain might exist at the same time. So what do? Many blockchains simply have a longest chain rule, which is to say new blocks must be appended to the longest chain, the longest valid chain that they've seen. And it's easy to know how long the chain is by looking to a common ancestor and seeing how many blocks back we are and making sure that they're valid. And if we keep this rule, then we know that if I see 2 different parties share with me their views of the world, one of them shares this one and one of them shares this one, then I will always choose this one. So we're talking about, yes?
Didn't you say that at the bottom or at the end of a series of transaction hashes, you put the hash of the previous block, and that's how they link together?
It's this one. So this is the previous block to this one.
Yeah.
Yeah.
So when you talk about the length, the longest chain, surely they're all just a number. Are you talking about the timestamp?
Yeah, the length of this one is 4, and the length of this one is 3.
But this is just a conceptual image.
Yes.
In practice, this is a 64 alphanumeric code. This is 64 alphanumeric code. This is. So how do you know if it's longer?
Well, it's not.
Or 256?
Well, it's explicitly not a timestamp, even though there might be a timestamp inside blocks, and some blockchain implementations have timestamps. But it's actually the number of blocks.
But when you say number of blocks, are there actually blocks, or are they all adding up to one hash, as you were saying a few slides ago?
No. The hashes are the components. So when Professor Rossi was talking about creating hashes and hashes of hashes, that's the Merkle tree that's associated with the hash for this block. And yes, the hash of the other block is represented inside of this block, is in this block,
Right,
but that's not.
But they are separate.
Yes, they are separate.
So,
Yes.
so 10 minutes or so worth of transactions, whether it's 1,000 or 2,000 or one transaction, however many, that are hashed together into a block, that block isn't then incorporated with another block.
It's not. The block itself is not in the next block. The blocks are separate.
So it's just the hashes.
Yes, there's a hash of block 2A in here.
Got you.
And there's a hash of block 1 in here. There's also a hash of block 1 in here. But we know that this block, that someone looking at this block can say, oh, well, there's a hash of block 2A, and there's a hash of block 1, and here there's a hash of block 1. They will be able to tell that these 2 views are different lengths.
So why are there different blocks? Why aren't all 4 blocks hashed into one again and again and again? Why is there a chain of blocks instead of one big hash?
Well, it's the set of transactions. So what is the property that we want? We want the property that when someone makes a transaction, anything that is done subsequently that depends upon that transaction is valid. And if my transaction gets unwound, then anything that depends upon it also gets unwound. So if I give you a coin and you give the coin to someone else, and then someone says that the coin that I gave you was wrong, that also means that the coin that you gave to someone else was also wrong. And that's a key property of these systems. And that is a key challenge to people who are looking to bridge gaps between distributed ledger systems. So for example, there are protocols such as Interledger, Overledger, Serenity, etc. Not Serenity, Cosmic, I think, is one of them. There are a number of protocols that try to reconcile across chains, but they all run into the challenge that fundamentally, the property that I want is that if my transaction gets invalidated by the community, then anything that depends upon it also must be invalidated. And that property within one chain is preserved. Because if we discover that the transactions in this block were transactions that depended upon this block, if we determine that 2B is not valid, then everything that depends on 2B is thrown away. And we go here.
When you talk about we, it implies a decision-making process.
Yes.
But actually the protocol makes the decision. So it's an automatic.
Yes.
Yeah.
Yes, that's right. So the key to this is that everyone rushes over to this one, because if they don't, they will be left behind. They won't be able to operate in the community unless they stay abreast of where the longest chain is. If they don't, then they will be left behind, as long as everyone is following the protocol. Yes?
Yes, but this now is a bit confusing. I thought that, also from the previous discussion, that one block, as soon as the community understands that it's not valid, it stops there. Now, whereas you say that we can go up to block 3, find that it's invalid, and then go back
Well,
and say, well, actually, all the previous
so
blocks were invalid.
So this goes back to the question about network partitions. Who is the community? How do we know when the whole community has agreed upon something? And that's the core question. When we have a closed system, and we'll get to this in a moment, and we know who all the participants are, then we know exactly what 51% is, or we know exactly what 67% is, or whatever our threshold is. When we don't know, we don't know. And all that we can do is make localized decisions. And how do we make these local decisions create the tendency towards a unified view? And that's the purpose of this protocol. Does that make sense?
So you mean that when we go to block 3, because the community may be dynamic in a non-permissioned blockchain and a permissionless blockchain,
Yes.
because it's dynamic and the composition of the community has changed.
Well, a permissionless blockchain, and we'll get to that also, but that's one example of something that can lead to this problem with getting everyone to have global consistency. A network partition in a permissioned blockchain can also lead to inconsistency.
But the point, I think, here is that block 3 is not the one that creates the finality. We are talking about even more blocks depending on the chain, right? So it can be 6, it can be 24, whatever it is.
Well, first of all, it's never final. It's never, so it's never final. The whole discussion about how many blocks it is to achieve some notion of finality are arbitrary.
But then I have one other question. So because there's never finality, it could be block 8. Block
Yes,
10,
because
whatever
the
in
property that
future.
we want is that if the transaction is invalidated, then everything that depends upon it is also invalidated. Yes?
Yes, Jeff, it's true that it's never final, but be careful because with this language, because it is to some extent is statistically never final. There is always a probability that the chain gets reversed, and this might make some people worried from, let's say, a logical perspective. But it is, after a while, in terms both of economic cost and in terms of time, it becomes completely impossible that the chain get reversed. I mean, it's the same, it's a statistical problem. They say,
Yes.
the molecules in this room are completely random, they can all go in that corner and we all die. That there is a finite probability for it, but there is more. So
Right.
it will not happen.
Douglas Adams.
Yes.
As much as, after 100 blocks, the chain will never reverse. It's just impossible.
Yes.
I'm having a question then.
Mhm.
Okay, I understand that. Then how does it know to what block?
Which one, the next, which do we
will have
append
go
to?
Back backwards, which was the validated block, to create a new chain.
Well, everyone knows, when they look at these two chains, everyone knows which one is longer. Everyone knows. Why do we know? Because we can validate, we can verify that this is valid and that this is valid. We can verify that they're both valid. So which one do I choose? The answer is the longest one.
I was wondering, maybe
Does that make sense?
more than 2 or 3 tails in block 1.
It depends. I mean, it really just depends upon what we see in the world. This is a sketch of what the choice of the longest chain would be.
Again,
Yes.
it is a community choice, and you can make the other choice. I mean, in this case, you make the other choice, they will become the same length, so you might win. But you have less chances to win. So either you have a good reason because you like a block 2 or because there is a wrong transaction that makes you profit there, or you will go for block 3.
But isn't
Because,
that,
I mean, if the equivalent choice, it's better to go for the longer because it's more likely that the other will go for the longer.
Yes.
isn't that when you create the fork, though?
Well, fork is a different, that's a different question.
Okay, but,
And
yeah.
we could talk about forks in the context of software, and we can also talk about forks in the context of splitting chains and having one group say, we believe in 2B, and another group saying, we believe in 2A, and then go their separate ways, as has happened with Bitcoin and Bitcoin Cash, and a number of other examples as well.
So in your
Ethereum,
scenario,
Ethereum Classic, yes.
What happens to block 2B then? If it's discounted and
Then the people who transacted in block 2B have to transact again.
again?
They have to do it again. That's,
And do they know that that's happened?
well, yeah,
And
because,
do they know
because they have the whole chain, so they know that people stopped using it.
So at what point in time do they
Well, that's what we've been talking about, right? So how much longer do the different chains in the system, how much longer does it, how many layers deep does a given block need to be before I know that everyone in the world is really believing it? And that's a question that is,
Also,
that there are some popular sort of community answers.
the transaction 2B might be taken by 2A and 3A. So it's not given that they are lost or they have to redo them. I mean, it might be that the 2A and 3A have to all the transaction, all the good transactions.
Oh, yeah.
So people
Transactions in,
don't get the orphan there,
so
so.
transactions in 2B might also find their way into these others anyway.
Maybe it's just worth talking about the memory pool of transactions when people or sender actually send a transaction to the network. They're all pooled in a pool.
Well, there are,
They're swimming around, flying around, and then miners essentially pick transactions.
well, these kinds of questions that we're discussing right now are, I mean, I hate to say details, but they give rise to different implementations. Many of these different implementations of this design, optimizations, choices of transactions, how many transactions per block, all of these kinds of questions are the underpinning kinds of questions of different architectures of blockchains. So this is a general scheme of what we're looking for and what properties we have, but many different implementations are different. And again, yes?
If 2B is invalidated, what happens to the miners? Is the accounting of the miner reversed and the money reimbursed to them? Or do they keep the money and then...
Well, what does it mean to have the money? They get the money in the block.
Yeah,
And if the block is invalidated, they never got it.
Yeah.
Yes.
So, yes. Yes.
Let's say something in block 2A, the transaction that is invalid,
Mhm.
because there isn't consensus. Meanwhile, there are additional transactions that are waiting to be hashed, etc. Is there like a red alert? Nobody. What happens when it's not green? If you know what I mean.
What do you mean? Well, what does it mean to be green?
Like when there's something that's not approved
Approved by whom?
by the community.
Well, that's the thing, right? We don't. This is about judging when something is approved. Like the central characteristic that makes this different from a distributed database, as I said before, is that we are giving up a guarantee of global consistency, and that means that
Okay,
we don't
let's-
know
Let's say you've got
when something is
40%
approved.
consensus, which is
Mhm.
definitely not enough. It's less than 51, less than 67, less than whatever. What happens to all other transactions that are happening afterwards?
Well, what do you mean? Like the transactions in the next block? You mean?
Yeah.
Well,
clearly it's invalidated, but these transactions have happened. They are on the ledger. whether
Well,
they're
they're,
hashed
well,
or
they're,
not.
well, the ledger is the chain. So if we start using this chain rather than this chain, then this is no longer part of the ledger.
I'm not talking about 2D. So in 2A, one of the rows is you've given him 1 Bitcoin for whatever, right?
Mhm.
But it wasn't validated. It hasn't been validated for whatever reason.
You mean it never became part of this block, you mean?
I think it means so the transactions and the hashing and the joining of the blocks continues even though
Yeah.
it hasn't been resolved.
Well, everything in this block has been
Exactly,
resolved.
because the real life, other people continue to do transactions, continue to put things on the ledger, even though 200 transactions ago there was something that wasn't valid. So what happens to it?
Well, people adding things to this, if people adding block 3A to block 2A is a statement of faith in 2A. Everyone who adds to block 3A, by adding to block 3A, you are believing in 2A. So everyone who is operating on block 3A implicitly believes that block 2A is valid.
Because-
Now,
and
whether
if they
this,
didn't believe, then they'll go to 2B or 2C or whatever.
or they'll create something different. Yeah, exactly.
Fine.
Does that make sense?
Yeah, thank you.
So the question then becomes one of, as Professor Asti said, well, how far does it need to go? How deep in the chain does it need to be for us to know that it's really done? And I think that that's a question for the community and how much of a guarantee that they need. People who need higher assurance might require more transaction depth. But in general, we can very quickly actually get to a state where we know that people aren't going to bear the cost of creating a completely new chain so quickly that they would wipe out all of these other transactions, because that is expensive to do.
How do we navigate between the blocks? So I understand that we need to select the chain that we trust, right?
You always choose the longest one.
Yeah, okay. So if you don't trust, we don't participate.
Well, if you don't trust it, yeah, eventually you won't participate, right? If you believe that block 3A is wrong, for whatever reason, and the whole world decides that block 3A is right, then you will be out of the system.
Exactly.
Or you will create your own new system of people who believe as you do. And that's how we
But
get
it's not
these kinds of
possible to
discussions.
understand the content of the whole chain. If I want to choose block 2A and see what's inside because I want to build a trust around the chain, can I navigate between the blocks?
Well, you could build something else that links to block 2A, but that's just a matter of what you happen to append to. It's like seeing a chain like this.
Reading the block, the transactions is this
You can read those, yeah. You can all of this is on the ledger. Everything that's been agreed to is available in whoever is keeping track of whatever that record is. So someone is keeping track of 3A to 2A to 1 to 0.
Right.
Someone is keeping track of this all. And if you want to believe in a particular block, you are implicitly believing in whoever validated that block.
And ultimately, there's no limit for the block size, for the chain size.
Yes. Well, yes, basically. I mean, you can get to these theoretical limits of the space of the...
Inside of the chain can be different concepts, different types of transactions. The supply chain can have the fleet management inside of a single chain, different business.
Well, these are use cases. This is different than... I'm just talking about the structure of the DLT. This is just about the data structure. There are many different applications. We need to move on. Okay, so consensus. So here we have an example of someone adding a block and the block propagating to everyone in the system, right? So someone over here added the block, and then the block propagated, and now everyone has it. Now suppose that two people add 2 blocks at the same time. Someone adds 2A, someone else adds 2B, and they propagate within their local groups. And then someone creates 3A. Well, anyone who had previously believed in 2A or 2B is now going to see this longer chain with 3A and is going to believe in that. And eventually that will come to dominate the whole set. So that's an illustration of what happens. So in general, a participant in the DLT, that is to say a voter in the consensus or a participant in the consensus, must validate the transactions before they can be added, which is what we were talking about. And what it means to validate depends upon the consensus model. Okay, fair enough. Now we get into these questions of permission versus permissionless that came up. What is permission? Well, in a permissioned DLT, I'm going to define this term. This term is actually in contention, but, but here for the purpose of this presentation, in a permissioned DLT, the set of nodes that can validate transactions are generally known, so it's possible to hold a vote. A vote, like a real vote. If I know who's voting, if I know who the voters are, then we can just hold a vote.
Know by name or know by number?
Does it matter? Just know. Know who they are. Know when I've got a vote from someone, I know that it's from that someone and not from someone else, and I know who all the someones are. In a permissionless DLT, we don't know who the voters are. So we need a way to ensure that the behavior of the system matches the expectations of its users, so that's where we come into these kinds of Sybil resistance, as people call them, or these kinds of proof of work, proof of something protocols. And we'll talk about how this works. But the idea was motivated by this notion of getting one person, one vote, but in reality we've seen that one person, one vote quickly de-evolves into one CPU, one vote, or one high premium ASIC cycle per time per vote. And that's not quite the same as one person, one vote, so there are problems with that. Okay, so let's talk about different ways that we can describe these DLT systems. First, we can describe different DLT systems on the basis of whether nodes are authorized to perform activities or not. So that is whether they're permissioned or permissionless. Or whether users are authorized to use services that might depend upon the DLT. Maybe that's public versus private. Maybe whether the services are accessible or discoverable. Maybe you can run a public blockchain algorithm inside a private network. These are all kinds of deployments that exist. That might also be called public and private. Whether governance is managed explicitly by a consortium or a federation, or maybe implicitly by a community of people who control the software, for example. And that's and these are the kinds of questions that underpin the choice of systems. So we can talk about these permission DLTs versus permissionless. This is sort of the way that I like to think about it. Permission DLT, nodes are explicitly authorized to conduct transactions, and here we get into these Byzantine agreement, Byzantine fault tolerance algorithms, which were the ones that Professor Asti mentioned were heavily studied in the 1980s and 1990s. And permissionless distributed ledgers, such as the Bitcoins and Ethereums of the world, where you have proof of work, which is really proof of computational power, proof of stake, like making big bets, proof of having wealth, and a variety of other systems. And we'll talk about some of those. Yes? Distributed voting. Oh, this is just the question of conducting actual votes over a distributed network. So there are lots of protocols for doing this. Certain kinds of file systems, distributed file systems, will often implement distributed voting. Groups in which you pass tokens to append to them and share them around a community and then collect them up at the end and then disclose them. Those are distributed voting algorithms. You can do that if you know who the people are. But if you don't know who the people are, then because they're anonymous, then you're over here. And this has some nice properties, but also some challenges. And we'll talk about some of those challenges now. Any questions? Okay, proof of work, the classic example, the one that Professor Asti mentioned. Bitcoin, Ethereum, Litecoin, Dogecoin, all of these, Zcash, Monero, all of these systems use proof of work, by and large. There are some exceptions, we'll get to those. The idea is that prospective validators solve a puzzle that is easy to verify, but hard to guess. And that is the key. So performing these dumb hash functions, hard to guess because you just have to crank through them in order to get through brute force the answer to your question. But it's easy to verify that you did it right. Because that's just one hash. Oh, I got it. That's right. So inverting the one-way hash function is a hard puzzle. That's assumed to be hard. And we can talk about quantum cryptography and solving non-deterministic puzzles separately. That's beyond the scope of this discussion. The point is that solving one of these puzzles is hard to do, but verifying that it has been solved is easy. The advantages is that cheating is hard, so everyone plays nice, basically. Disadvantages is that ultimately the network will tend to be run by those who can guess more. And if you build an ASIC or a cluster of ASICs that fills an entire warehouse in someplace in Inner Mongolia or Argentina or take your pick, then you will be in control. And there are mining pools in the case of Bitcoin and some of these other proof-of-work systems that people have argued are actually under control of a very concentrated set of individuals or groups. And ultimately, and another property is that we have that zero-sum arms race associated with being faster than the next group. And that raises some of these questions about the environmental sustainability of these kinds of systems or the negative externalities more generally. So we have some alternatives. People recognize that proof of work is not so good. So what else could we do? Well, we could do proof of stake. And here are some examples of the Serenity version of Ethereum, Tendermint, and a few others.
Could you
Yes.
explain what proof of work we covered? Could you remind me what
Proof of stake.
was?
Well, that's what we're talking about now.
Oh.
Right. Yeah. So prospective validators deposit tokens in exchange for the chance to be selected for block creation. So if a validator produces a block that's added to the chain, he gets a reward. I mean, that's just like in proof of work, but except that it's based on a bet rather than being based upon proof of having done some brute force algorithm for a long time. So the idea is that if we use proof of stake, then maybe we can save on some of the negative externalities of environmental costs, and maybe we can get something more fair. Of course, the problem that maybe some of you have noticed is that if you have this casino and you wind up allowing big players to demonstrate to vote more, they're going to be the ones in control. And they are. I mean, it's energy efficient, but those with the most tokens who can place the most bets, their interests might not necessarily match the interests of the users of the system in general, and that's the disconnect here. So if we think about this as kind of a search for the right democracy, it's not clear that this one is much better than the other one and might even be worse.
How do they get most tokens?
What?
So how do they get most tokens and then they place the most bets?
Well, if they have more, how do they get more tokens to begin with?
Yes.
Well, they might mine. They might receive tokens as payment for external services. Money can be exchanged for goods and services. People might pay them for something else, and then they have more tokens.
So the proof of stake.
They might buy them.
The proof of stake starts with the people who have the most tokens.
Well, those are the ones who can place the most bets. The people with the most tokens can place the most bets. If they place the most bets, they're in control. Does that make sense? Okay. Delegated proof of stake. So that's like proof of stake, but except, well, this is the question of, well, some people might argue that then the relatively rich people are in control in this case, right? So why don't we have everyone elect their feudal lord who can actually vote in a much more unified kind of set of parties, and there are some examples of that. Okay, so you can elect a representative, and the representative takes the votes for you. More scalable, faster, maybe more fair, but actually it's even more centralized, right? Because now you've got that pool of very wealthy voters who are making all the decisions, and all that you've done is create a kind of a tiering, a class system, if you will. So that's really possibly not so good either. Proof of capacity. Now here's another one. Say, okay, proof of stake doesn't work because it's easy to get, because tokens are distributed unevenly. Proof of work doesn't work because CPUs are distributed unevenly. So maybe proof of capacity, hard drives, will make people buy hard drives. And people who can prove that they've got the most hard drive capacity can solve puzzles that require them to have this really large hard drive. So it's based on the space. Advantages: storage space is more of a renewable resource, at least. You can reuse the hard drive, which is nice, unlike CPU cycles. But it's still pay to play. Right? You can still buy more hard drive space. You can still wire them up. You can still have your hard drive space really be Amazon cloud servers and all of these sorts of things. So it doesn't really solve the problem. Here's another one that I like. Proof of elapsed time. So Intel said, okay, we're going to solve the problem. We'll create this specialized chip. And the specialized chip will only be manufactured by us, and it will have embedded cryptography, and it will make assertions on the computations that you do that you have weighted, that your CPU had basically done nothing for a certain period of time, and we'll be able to have our tamper-resistant CPU assert on its own accord that you had actually let its CPU idle for some period of time, right? So not burning up the world. In fact, you're doing nothing. And as long as we trust Intel's chip, then everybody who uses this protocol will be happy, right? Well, yeah, maybe. You have to trust a lot of things. You have to trust the trusted computing paradigm itself, which is possibly true, possibly not. You have to trust Intel to actually not only do you have to trust Intel not to design the system poorly or with bugs, but you also have to trust Intel not to furnish shed loads of these chips to parties that they happen to like. So, yep, the only way to beat the system is to get more chips, but of course, there are a lot of people to trust in the way of that. That make sense? Okay. All right. So I'm not so sure that these are all that different. So just going back at some level, this concludes the list of examples that I've shown you. There are more out there, but they're all these kinds of techniques to try to make one person, one vote that don't really work, or that have fundamental flaws. But nonetheless, people use these systems because at some level they work.
Where is the Tezos and Cardano?
What?
Where are they in this consensus mechanism? Tezos and Cardano.
What do you mean?
Tezos?
Oh, Tezos. What kind of system does it use? I don't remember.
And Cardano?
I don't know. You can look it up. I don't have that. I don't have the answer to that. Sorry. Yes.
So are these consensus models still being created, and is that something that someone can create? Or are these consensus?
Well, you know, you can create. Okay, so you can take these paradigms and you can build these kinds of systems with software. Yes. You can also create your own consensus models that look like this. Of course, people do. I mean, they had to come from somewhere. But at the end of the day, these are properties that you're trying to achieve these kinds of democratic-like properties, even though in general they have these flaws. And clearly there is opportunity for improvement, but it's not clear that that improvement will actually constitute much. So Byzantine fault tolerance, Hyperledger fabric. Basically, if you have these real relationships, then the identities are well known and they're registered in a central registry, scalable. It has better security properties, more robustness. So this kind of system, you know who the players are, but of course that means that you're in this permissioned kind of consensus algorithm and you're trusting some notion of federation to accept who is in and who is out. And unless everyone agrees on who is in, it's very hard to break in.
So this is kind of an example of a private?
Yes, could be considered private. I'm using the term permissioned for it.
Yeah.
And I defined earlier in the presentation my choice of terms. But some people call this private. I mean, this is about the terms that people use. And you can implement this in a private context pretty easily. Yeah. So often there's some overlap between these notions. And there's also this idea of federated Byzantine agreement. So, you know, here you have this notion of these unique node lists or slices where you're not trying to achieve global consistency on who everyone is, but still these kinds of localized networks of consistency that might overlap in different ways, which is nice, but it adds some complexity. So that might limit the set of applications that might be useful. And participation is open in theory, but not necessarily open so much in practice because you have to be part of an organization. So it remains to be seen whether this is better than the others or not. But I think that there's some good argument for why that might be so, because you do have this combination of open participation without this prior membership of a consortium, which is a nice feature for a permission system. And I would argue that if we had the choice of a permission versus permissionless DLT, I would rather have a permissioned one for implementing anything that I really care about. Because with a permissionless one, you never really know who is going to take over the system. And this is important when we talk about ICOs. Now, protocols, we talked about forks, soft forks. This is just a term that people are using. Backward compatible nodes running the old software can still participate in the new system. Hard forks mean they can't, and you just have to split. Examples of hard forks are we had Bitcoin Cash, Bitcoin versus Bitcoin Cash, Ethereum versus Ethereum Classic. These are examples where people actually did say, nope, you know, the protocol changed, but I believe in 2B and not 2A, and that's that. So there was a point where the two chains had common ancestors, but they diverged, and that was that. And they were coordinated because different groups of node participants had different software and different processes for gating changes to the software. They split. And it makes sense how they split. They just effectively said, we're going to play by different rules. And we're going to believe in this block, and that's it. So IBM came up with a list of good questions to ask when we talk about use cases. What constitutes a good DLT use case? Is there a business network? Do you need consensus? Do you need an audit trail? Must the record be immutable? And must dispute resolution be final? If you have all of these properties, then DLT is appropriate. If you don't, maybe it's not. And they would argue that you need to have at least 2 or 3 of these, I think, in order to even consider using DLT. But basically, the idea is that if you don't have these, if your problem space doesn't have these properties, then you might be better off with something else. You might be better off with a distributed hash table. You might be better off with a database. You might be better off just talking to each other or just having a centralized ledger. So DLT is not for a universal solution to every problem. Yes?
So in the case of Bitcoin, what would happen in the business network?
Well, the business network is people exchanging money. Do you need consent?
Start with a business network.
Well, at some level it did, right? Because Bitcoin was intended to be a mechanism for exchanging money, for transacting, which is absolutely about business.
But the network didn't exist. I mean, it was created thanks to.
Well, it was created with this in mind. It was created with these problems, this problem space in mind. So applications, payments, clear and settlement, those are the business network examples. Trade finance, maybe you want to figure out who is who is joining up to a trade or what a marketplace needs to look like, could be distributed. Contract negotiations, multi-party, tracking assets, so we talked about supply chains. Decentralized identity management, that could potentially be done using DLT as well.
Sorry, what?
Yes.
Could you explain that?
What?
Decentralized identity
Management.
data management
Mhm.
on DL. So
Yeah, so someone could put credentials on a DLT, and then you could ask someone to verify based upon the DLT that your credential is valid. And the nice thing about that is that we can separate the party who issued you the credential from the party who validates it. And that's nice to be able to do if you're concerned about that party who issues you the credential tracking all the times that you have to be validated.
but if somebody hashed who you are to a number,
Well, that's not okay, because we can't put hashes of identities on the DLT, because then when someone guesses that it's you, then they can prove that it was.
so
They can prove that it was you forever.
So in that case, I don't understand what you mean by personal data management.
Well, these are systems that can be used to facilitate you being able to keep the metadata of your different transactions isolated. You can actually manage who gets to see what transactions you've done.
Give the
Yes.
example of the source of the supply chain. So
Mhm.
a producer, you want to
Yeah. So this is
certify the producer, the address, the name of the producer, and put this as a.
well, this is just going back many steps in the supply chain. Unfortunately, we need to move on. And the idea of being able to disaggregate the original suppliers from the subsequent chain suppliers. So in modern supply chains, most of the time, the intermediaries will aggregate all of their sub-suppliers, if you will, And then I, as the purchaser from that intermediary supplier, can't tell where they came from before that.
Yeah.
With this kind of system, I might be able to do so, which is the opportunity. So there are different ledger architectures. So I encourage you to look these up. I have some nice links here. IOTA, Byteball use generalized, decentralized acyclic graphs. Lightning Network and a few others have these state channels, which are basically like correspondent banking. They're sending a channel through the network, and the transaction is not consummated until it's done. Automatically executable contracts. Sometimes people call these distributed applications or DApps or smart contracts. Yes, there's a history to this as well. I think this was Nick Szabo and others. Here is a link. Ethereum likes to create a mechanism for this, which is an interesting use of DLTs. So what we're doing here is we're basically encoding a procedure that we can actually run and have the nodes on the network run it rather than the party who wrote it. So I can put it on the network and have the other participants in the network run it. So removing me as the issuer of some contract doesn't necessarily mean that the contract won't run. So people have talked about this as a way to, for example, facilitate factoring of transactions where people make payments at a certain time. You can use this to guarantee that the payments will be made on time. And here are some examples. ICOs, we talked about exchange tokens, which are made for the purpose of facilitating transfers of money. Security tokens satisfy the Howey test. This was actually a rule in the US that was used to distinguish security tokens from other tokens. Investment of money in a common enterprise, and also an expectation of profits from that. If it has those two features, then it's a security. That was the idea that was used to characterize security tokens. And utility tokens, by contrast, were about future access to a company's product. So that's like customer financing. So think about an airline manufacturer like Boeing, for example, or Airbus, that before they start construction of their new aircraft, they want to know that they have a customer who's going to buy it. So the customer might actually finance in advance the construction of this new aircraft. Utility token is that kind of approach. Think of it as customer financing. Governance models. Questions of who's in control. Permission DLT might be controlled by consortiums or gateways who might be like market makers. In permissionless DLTs, we talked about some of the parties who control it, might be mining pools or wealthy participants. So there will always be gatekeepers, right? So the question is, who is in control? Are they institutional, or are they sort of natural law, if you will? So these are questions about the design of these systems and the governance of these systems. And this slide is where I like to talk about some examples of how people have applied DLT in cases that don't really benefit from DLT. Smart contracts as a replacement for law. So many of you may have heard of the Decentralized Autonomous Organization, or DAO. With the idea that code is law and law is code. The DAO basically had a major bug that was exploited by some parties. They might have been hackers, they might have been insiders, we don't really know, who were able to do an ICO, collect real money, and then take all of the wealth from all of their backers and walk away with it. And that was a problem. And they cited the idea, well, first of all, we don't know who they are because it was autonomous and decentralized, and who knows. But the idea was that, well, code is supposed to be law, and you're trusting the code. But the problem is the code might have bugs. It might be run in someone else's execution environment. It isn't really a replacement for law. Second, some people like to look at DLT as a decentralized network in the cloud, a decentralized database in the cloud, a universal database for storing data. And there have been some insurance companies that have sought to use public ledger to access and aggregate private data. So for example, some medical insurers have looked at DLTs as a way to pull data out of general practitioners' offices and put them in places where they can just say, hey, it's in the public domain. Well, that's Seems like an obvious trick. And another example that I think is kind of sad is sometimes people say, hey, let's use a DLT to improve our reconciliation across desks within our two groups. But the problem is that when people start working together to build the DLT, they often find that they are cooperating really closely and they don't really need the DLT anymore because they're no longer really at arm's length. Well, I guess they could have done that better or more efficiently. So I'd like to argue it's really about decentralizing control and eliminating control points. This is the second to last slide. It's not about efficiency. Databases are faster. Distributed hash tables are faster. Working together with your neighbors is often faster. It's not a substitute for appropriate governance because who knows who's in control. Networks are often not as distributed as they seem. We assume that Bitcoin is well distributed, but actually it might not be. It might be in the hands of small mining pools. And it's not a universal database in the cloud. That's just not what it's for. That's not the problem that it solves. Now, what is it? That said, there are real uses. It might offer the tools for privacy-enhancing marketplaces. Might allow for regulators a means of disintermediating certain monopolistic markets. And it might actually replace some legacy systems that are themselves not really efficient and don't work so well. So there are opportunities, but we need to be careful in identifying what they are. Do we have any questions? That's it.